Our webinar starts in 1 minute. Hello, everyone, and welcome to our webinar. My name is Igor Nemet. I'm an application scientist at Bruker Nano Analytics. I will be your host today. Today's webinar title is Transform Challenging EDS Measurements into Routine Analytical Work. Before we start, let me give you some housekeeping details. You should now see the introductory slide on your screen. This webinar is interactive. The presentation will last about 40 minutes. You can ask questions at any time according to question and answer window on the right side of your screen. Please press send and then we'll receive them. Then after the presentation, we will move on to the Q&A session. If we are not able to get to your questions during this live event, we will follow up with you by email. Please note that this webinar is being recorded and will be available very soon for on-demand viewing. Let me now introduce our speaker, Dr. Poover Soni, who began his career with Bruker in 2019 as an application scientist. Poover has brought substantial knowledge and experience in the field of analytical electron microscopy from his doctoral research work from RWTH Aachen University and Max Planck Institute in Düsseldorf in Germany. During this time, he worked extensively on analytical electron microscopy and nanoscale characterization of semiconducting materials. As an application scientist at Bruker, he works on different techniques, including EDS, EBSD, and TKD. So let me give the word to Poover, who will start in a second.
Thank you, Igor. So welcome, everyone. So today's webinar will be transforming challenging EDS measurements into routine analytical work. And what I'll be presenting today is, And this is the outline of the talk. I'll start with the basics of SEM EDS signal, how it is generated, and what affects the data quality during imaging and also during EDS mapping. We'll discuss shortly how solid angle and detector geometry also affects the signal collection. Then I'll present how FlatQUAD compares to conventional inclined or large area detectors. And that will be followed by application examples where I will show how FlatQUAD can be used at very low probe currents for EDS analysis. And then we'll end the session and the webinar with summary and Q&A session. So then basics first. So let's see how signal is generated. Of course, if you are working with electron microscopy, you know this. So primary energy electrons, they hit a material, they interact with the material, and they generate this interaction volume, generating different kind of signals. And what we are interested today is secondary electrons, backscatter electrons, which generates SE and BSE images, and characteristics X-rays and brainstorm X-rays, which together give us an EDS map. So an SEM image typically has pixels in X and Y, and these pixels multiplied by the total number of by the dwell time or scan time, so to say, per pixel will give us the frame time. So here it's 2.6 seconds, and the difference between SEM imaging and EDS mapping is that EDS maps are overlaid. Several EDS frames are overlaid, over each other to form a map. So if the acquisition time is say 10 minutes, then for these conditions we'll have about 230 frames. Very simple. So it depends on the type of sample that you use and the type of analysis. So if it's simply imaging, then it may be easier. But if you are doing analytical work like EDS or EBSD or even TKD, then the probe current and dwell time, or let's say the exposure time, must be carefully adjusted. Now, if you have a charging sample or a beam sensitive sample, then longer dwell time may give you better signal, but then there may be a very strong charge accumulation or charging. And if the sample is beam sensitive, then there might be damage of the sample by the beam because of the local heating. So there is option to do coating of the sample, or maybe use low pressure mode in SEM if you have the option. But coating is either not allowed or maybe it's not feasible for many materials. And low pressure mode in SEM, they usually give very poor signal to noise ratio, and for imaging and even for EDS, the signal is very low. So now for, let's say, for 10 microseconds and 100 picoampere, we'll have about 6,000 electrons per pixel. And now if we decrease the dwell time from 10 microseconds to 100 nanoseconds, then we'll get 62 electrons per pixel. So this is simply by decreasing the dwell time, the number of electrons reaching per pixel on the sample is now much, much lower, 100 times lower. So this will avoid charging and also sample heating. And this may be better for the sample, but then the signal to noise ratio is very bad. So then you get maybe very noisy SEM images, and sometimes even no EDS signal. And the story is similar for high spatial resolution measurements. That high probe currents are not ideal for high spatial resolution measurements. So we have to use lower probe currents to minimize beam divergence. And if we use high probe currents, if with high probe currents, the interfaces are blurred and also the fine features are not visible. So then we really need low probe currents to get the very good spatial resolution. But then again, the signal is very low, and signal generation is low, and also the images are very dark. So then now let's take the 100 picoampere and 10 microseconds as beam parameters, and let's calculate how many electrons are reaching the sample. So the total charge will be total charge for 100 picoamperes probe current, and dwell time of 10 microsecond will be this multiplied with this, so 10 power minus 15 coulomb. And if we divide this by the elementary charge or the charge of a single electron, then we get the total number of electrons, which is around 6,000 under these conditions. And now, if we have an image of 512 by 512 pixels, then we will have 1.63 billion electrons per frame. So then this means that for beam sensitive or charging samples and high spatial resolution measurements, the problem is the same, that the signal generation is very low, simply because we have a very low electron budget per pixel and per time. So now let's see that how many photons are collected within EDS detector. Previously we had a number of 6,000. Now let's round it off to 10,000, just for simplicity. So the number of characteristics X-ray generated for 10,000 electrons is 10. This is just by the rule of thumbs, and this depends completely on the material density and also the primary electron beam energy. So we'll have 10 X-ray photons for every 10,000 electrons. And this is for the whole solid angle, which is 4 pi, but we only get X-ray emission in the upper region, which is 2 pi. The bottom 2 pi, the X-rays are completely absorbed. So the solid angle for this for the whole region, which is 2 pi, is 6.28 steradian. And now let's say we have an EDS detector of 100 square millimeter chip size, and the separation between the chip and the sample will be then approximately 40 millimeter. For this is typical for EDS detectors of this size. And then if we use a very simple formula for solid angle, of course this is not real. This is the real formula is quite complicated, but let's for simplicity let's use the basic formula. Then we'll get a solid angle of 0.0625 steradian. And if we want to now calculate the solid angle fraction for this EDS detector over the whole 2 pi solid angle, then it will be this divided by this. So then it will be 0.01, which means that we will get one X-ray photon collected for every 100,000 incident electrons. So then this means that what to do if we want to improve the signal. So can we use large error detector for higher solid angle? Let's also do this calculation. So instead of 100, now let's double the size, 200 square millimeter chip size. And then because the detector is quite large, you have to place it quite further away from the sample. So instead of 40 millimeter for 100 square, you have maybe now 60 millimeter. And then the solid angle using the same formula will be 0.05 steradian, which is even less than a 100 square millimeter detector. So a large error detector does not naturally mean that you'll have better solid angle. And what you could do is that you could maybe, if you have free ports, you can have 2 or 4 detectors to improve the solid angle, but still it's quite low. So then problem with conventional detector geometry is that the solid angle is very small, and also the elevation angle is very, very shallow. So we are collecting X-rays where the signal is very diffused and heavily absorbed. So if you know that the signal intensity drops as we go from 90 degree to 0 degree, and we are collecting at around 25 to 35 degrees elevation angle. So the signal intensity is quite weak at these elevation angles. So then what to do? So let's say if we have a detector which is inserted right under the pole piece, very close to the sample, let's say this, then we have a very large solid angle of around 1 steradian, just because the sample and the detector are so close. And then we gain, with the single detector, we gain 10 to 20 times higher solid angle as compared to a very large error detector, or even let's say 4 large error detectors. So yeah, this is exactly what FlatQuAD does. So it is a side entry EDS detector, which is similar to a retractable BAC detector. And it is optimized for maximum signal conduction, where the intensity is also the highest. So at very high takeoff angles. It also has a 4-segment design. So you are measuring everywhere around the sample. And for shadowing or topographic samples, the data is not lost just because of sample topography. And because of the very short sample to detector distance, you have a very high solid angle. And with the highest takeoff, with a takeoff angle between 70 and 48 degrees, so averages to 60 degrees, we have very high collection efficiency because we are measuring where the signal is the strongest. So this is ideal for low kV, low probe currents, and even high kV, low probe current measurements, where samples they cannot. We have to keep the probe current budget low to to get maybe lower charging or get the best resolution. So this gives us a higher sensitivity. All these factors together, they give us the highest sensitivity. And with the FlatQuAD, you could have output count rate as high as 1.6 million counts per second. So then let's see some ultra low probe current examples. This is a pharmaceutical tablet which was charging heavily, and because of this, I had to go to the lowest possible probe current on the microscope. It was 18 picoamperes at 5 kV. So this is what I got. So this is at 5 kV, 18 picoamperes. I got high count rate of 3,100 counts per second, which is very good considering the very gentle probe conditions. And this is the full X-ray intensity map. So we can see that the sample is highly topographic, charging, and there are at a very low probe current, and we still have a very filled X-ray intensity map. And yeah, it's there is barely any shadowing. There is only data which is missing from the cracks. And this is the SE overlaid chemical map, and this is the composite EDS map. So yeah, you can see how nicely all the features are resolved, even at such low probe current for a heavily charging sample. And this is insulating sample measured at high vacuum to get high spatial resolution. So this is a cable sample, and we know that cables have very heavily insulating layers. And we can see how nicely we could map with the FlatQuAD because of the high sensitivity. And at low probe currents, I could, even at such low probe currents, I could get an output count rate of 71,000 counts per second. Now, if we zoom into this region, then we can see that there were small magnesium particles which were less than 1 micron, so between 100 nanometer and 1 micron in size, and we could resolve this because we were at high vacuum conditions to get the high spatial resolution. And again, super high count rate, and the measurement was only for 30 seconds. And yeah, because of the very high sensitivity, I only needed 30 seconds to measure this region. And if you see that there are some cracks and crevices and valleys in this material, so if you zoom into this, then you can see. So with the FlatQuAD, because of the annular four-segment design, we could measure around the sample, around this layer, and also in the valleys. And if we compare this with a conventional detector, then we can see that there's a strong data loss from around these copper wires where tin is coated. So yeah, this is what you gain when you have a four-segment detector and you are measuring very close to the sample. That data loss is very low because of shadowing or topography. And also because of the high count rate for this measurement, I only had to measure for 5 minutes, but because of the low count rate of a conventional detector, I had to measure for 30 minutes. And this is a radiolaria, which is a single cell algae, which is typically found in ocean. And they form this beautiful and very intricate silica skeletons that you can see here. And they are very important for studying actually atmospheric carbon. And what they do is that they store these information within them, and then we could also get information on water temperature history of the ocean and also the salinity of the ocean. And what happens is that once they die, they settle, they sediment at the bottom of the ocean, and they could be recovered to see historical water temperatures. So yeah, the sample was measured without any sample preparation. It was heavily charging, but still I could measure this without any problems. Moderate to low probe conditions, and still very high count rate. And this is another radial area, and you can see that the shell is part of the shell is still intact. And yeah, again, I could measure with the FlatQuAD without any problems here. And this is to show you how nice the collection efficient the shadowing and topography is minimized with the FlatQuAD. That if we use FlatQuAD, we get the full X-ray intensity map, and there is collection from all the sides of the sample. But with a conventional detector, um, because of the shadowing, we barely get any signal here. And also, you can see the signal to noise ratio is quite good with the FlatQuAD, but quite poor. So the background signal is almost equal to the signal from the material. And also you can see the difference in count rate under same probe conditions. So with the FlatQuAD, I could get 96,000 counts per second. And with the conventional, it's only 2,000 counts per second. So 50 times more signal with the FlatQuAD. And this is an anode cross section uh, measured with the FlatQuAD and with the conventional detector at 12 kV and 1 nanoampere. You can see the enormous output count rate that I get for these material, and with a conventional detector, it's barely 20,000 counts per second. What is interesting to see is that we have very good signal collection, and the data from let's say shadowing of the material is all there, but with the conventional detector, there's a lot of data loss. And because of the high signal to noise ratio and also the 4-segment design, I could see particles which were there, but the data was not there because of the inclined detector geometry. So here you can see these two particles. They can be seen with the FlatQuAD, but with a conventional detector, we cannot see them. And here also you can see that the difference between the noise, which is in this region, and the signal is almost the same. So that's why you see more noise, but the signal to noise ratio is very good for the FlatQuAD, and that's why we could see these particles very nicely. And this is a bulk FinFET device of bulk FinFET semiconductor sample, and it was measured at 5 kV and probe current of 1.1 nanoampere. And we can see the very high count rate of 305 counts per second, 305,000 counts per second. And because of this very high count rate, I only had to measure for 90 seconds, and I could get this very high, very good statistic map. And I could even resolve a feature which was around 6 nanometer in size. And if you're working with semiconductors, then you know that there is a very strong overlap between silicon, hafnium, and tungsten at around 1.7 kV, and we could easily deconvolute this with Bruker SP software. So this is an inbuilt function in Bruker SP software. You just click, you just do one click, and it is the maps are deconvoluted automatically for you. This is a STEM sample. So again, a FinFET device, but with 14 nanometer node technology. Electron transparent sample, and the thickness of the sample is only 30 nanometer. And you can still see how nicely we could see all the layers. Again, there is a strong overlap between tungsten, silicon, hafnium, and tantalum. We could still separate them. Of course, tantalum was used for tantalum L lines were used for this map. And this was acquired at 25 kV and low probe condition, so low probe current of 300 around 300 picoamperes, and still I could get 58,000 counts per second for a 30 nanometer thick lamella, which if you work with these kind of materials, you know how poor the signal is if you are working with EDS and STEM in SEM. And this is at even higher magnification, so you can see the feature that is there. So the tungsten layer that is here, physically, it's around 1 to 2 nanometer. And the EDS spatial resolution that I've got here is around 4 nanometer, which is quite good, considering that this measurements are done in SEM and not TEM. And this is a boron nitride standard sample on a brass block. And we can see only 3 kV measurement and very low probe current and still very high count rate. And after quantification, we can see boron and nitrogen, they are 1:1. Of course, I placed, I set carbon and oxygen and the other contaminants as deconvolution only. So then they are automatically set to 0%, giving me boron and nitrogen quantification only at 1:1 stoichiometry. This is a biological sample which was washed with gold nanoparticles. And yeah, we can see the gold nanoparticles very nicely. And if we do phase analysis, we could extract spectrum from a single phase. And yeah, this is what we see, the gold spectrum from the gold phase here. And this is a dinoflagellate, so again, a biological thin section, around 100 nanometer in thickness. And we can the problem here was that these bright particles, they were always seen in SEM, but it was never EDS. Conventional EDS were not able to see what material it is. But with the flat quad, low kV, low probe current, only 6 kV and a few hundred picoampere probe current, I could see this within a few frames, in a few seconds, that this was clearly nitrogen. And the output count rate at these general conditions was also quite high at around 300,000 counts per second. And you can see that, yeah, this is a biological material, so it will always have light elements in it, and all the light elements like nitrogen, carbon, oxygen, and potassium, sulfur, phosphorus, all are also there. So these were some benchmark tests that I did with the flat quad. So I used the lowest possible probe current on a copper sample at 5 kV, and I wanted to see how much input and output count rates I got. So mainly input count rate. So at 18 picoamperes, I could get around 8,000 counts per second. And at 237 picoampere, it was over 100,000 counts per second. At 1.3 nanoamperes, it was 600,000 counts per second. And at 5.2 nanoamperes, it was 2.1 million counts per second. So I can say that if I scale this down, then I can get approximately 4,600 counts per second at 10 picoampere for copper at 5 kV. So if you want to see, if you have an EDS system, if you want to see how many counts you get per picoampere, then you can use simply copper tape, and you can also see how your EDS compares with the flat quad. So then with this, I reach the end of this webinar. So to summarize, I would say that flat quad has highest solid angle for SEM EDS. It's 1.1 steradian because of the sample detector geometry. It sits right above the sample, and this is why the solid angle is so high. And if you combine this with the high takeoff angle and the fast electronics that we have, then you can get very high signal to noise ratio for EDS measurements. And this detector is ideal for challenging samples where you really need low kV and very low probe currents, and still get very high resolution, and maybe also minimize charging for let's say beam sensitive samples. And because of the low probe currents, you can still use the high vacuum conditions, so you don't compromise with spatial resolution here when you use the flat quad. And with the four segment design annularly placed, you have no problems if there are topographic samples or shadowing samples. So yeah. And also with I also showed that you could detect as low as boron with this detector. And this could be used also for pre-screening of fib and TEM lamella in SEM. And since we only use very low probe currents, it could be used to minimize charging samples or sample damage, and it minimizes carbon deposition on the samples. So yeah, thank you for your attention, and we are now open for the question and answer session.
Thank you, Purvesh. Yeah, thank you very much for the nice explanation, detailed explanation, and the nice examples. And as you mentioned, we will now have our question and answer session. It's going to take like around 10 minutes. And here, first, quick reminder to everybody: you can still submit a question by entering it to the Q&A box. So please do use the Q&A box and type your questions and press send. The first one, I think it was asked when Purvesh started with the examples. I think you were partly already answered, but maybe just for recap. I wonder how you deal with sample topography. I'm talking about the first application example, the pharma sample, for instance.
So yes, with the sample topography, we are measuring all around the sample with the 4-segment design. So imagine having 4 EDS vectors on all sides of your chamber, and because you are measuring from all the sides, you don't miss any signal if there is shadowing or topography in the material. So an easy way to look at this is that if you have a topographic material, and if you are shining light from all the sides, then you will not have any shadowing. So it's a similar analogy. So you can also measure from all 4 sides, and then you have no shadowing or topography. Yeah.
Okay, thank you. What kind of SEM do you need for the detector? Can we use an older tungsten filament SEM, or do we need field emission for this? So the general answer for that question, yes, in fact, you can use. It depends on that's what can be mounted, inserted, attached to any practically any microscope chamber on a horizontal port. If you have a certain type in mind, you just let us know which type of microscope you mean, and then we most probably already have the adaptation. If not, then we look it up in our database whether it can be mounted. Okay, then we move to the next one. We have a couple of questions about whether can you use BSE detector with the FlatQUAD? So if yes, then how?
So yeah, you could use an in-beam BSE detector, but a retractable BSE detector would sit at exactly where the FlatQUAD is. So you have to retract the BSE detector if you are using the FlatQUAD. And yeah, so I think that's what you wanted to know.
There's one direct question concerning to one of the examples you showed. So what was the image size and dwell time for the FinFET map you showed?
The
Maybe you stated it on the
bulk. So FinFET bulk, if you are speaking of the FinFET bulk map, then I believe the image size was 300 by 250 pixels, and dwell time I cannot recall exactly, but maybe it was around 8 to 16 microseconds.
There's one question about, I think it's still the semiconductor, the FinFET sample. Maybe, so how did you perform the deconvolution you showed at about 1.7 kV?
So yeah, that was the peak overlaps between silicon, tungsten, and hafnium. So silicon K overlaps heavily with tungsten M and hafnium M as well. What we do here is that we have the atomic database, and we know the theoretical line intensities. So we could use these mathematical models to deconvolute the peak overlaps and then assign the deconvoluted peaks to the pixels that it comes from. So this is how deconvolution is done in S3 software. Okay, then this question is that how do you
Okay.
how do you deal with the incident of backscattered electrons in EDX sensors? So we have an energy filter which is always there on the chip, so that filters out most of the backscattered electrons. Um, and we also have different energy filters which could be inserted and retracted at different high voltages. So you're not limited with just one high voltage. You could go to low kV or high kV depending on the application. So I showed you application examples of 3 kV and also 25 kV. This next question if you could give.
So we have one more question. You showed some examples where the high resolution SE or SEM image was a bit of noisy. Can you tell maybe why? Comment on that.
Yeah, so these images were noisy because I was using electron transparent samples, which were only 30 nanometer in thickness, and I was using SE or in-beam SE mode. Typically, what you do is that you use STEM detectors for these kind of electron transparent samples, but I was not using STEM detector. I could use them. I was just using the SE modes, SE mode to minimize the stray radiation or the system peaks which could be there from the chip of the STEM detector. So that's the reason why the image quality was poor. And that was also discussed that typically if you're using just a regular SE or in-beam SE modes and you don't have much signal because of the very low probe current. And that's also another reason that the image quality is poor. But what we need here is not the SE or BSE image quality, but the EDS map, which was the best resolution. So yeah.
Maybe we have time for one more question. We have actually several questions regarding this topic. Let me combine those. So the questions were about the BSE detection. So usually BSE detector is used for charging sample. Can you use the BSE detector with a FlatQUAD detector? So how you deal with this? Let me take the question. Maybe let Purush comment on this later. Yeah. If it's insertable retractable BSE detector, that in most cases it will not be available when the FlatQUAD detector is inserted because they are both sort of taking the place below the poppies. So in that case, you can do sequential analysis, so do a BSE image and then do the EDS analysis. But actually, so what we our point, the Pur's point was how I interpret it, and he even showed a lot of maps where using this type of detector, the EDS signal strength is so high. There's so many counts. You can even tell apart the fine structures you are interested in the sample. So actually, what you would use the BSE image or the BSE contrast for is could be almost neglectable. You have you gain a lot more information using the real material, the real elemental signal. Yeah. We have one more minute. Let maybe take this one. The question is about how far or how close can we get to the sample?
Yeah, so I showed in one of my slides that the sample to detector distance is around 2.5 to 3 millimeter. So that is not the working distance, but that's the distance between the sample and the detector, which gives you the maximum solid angle or the maximum counts. Typically, you can go as low as around 8 millimeters, 7.5 even for some microscopes, depending on the port position. So yeah, you could even go to very long working distances where I have measured very high resolution EDS maps at 13 millimeter working distance without any problems. And you can also go low to around 8 or even 7 millimeters if the port position is proper. Yeah.
Okay, I think Our time is unfortunately up, so we are now concluding our question and answer session for this webinar. At this point, I would like to thank again Purvesh for the very interesting, nice content, the examples he showed, and the explanation of this detector type. And for you as a reminder, today's event has been recorded and will be also available on our website for download for on-demand viewing very soon. So thank you for being with us today, and we hope you're with us at future webinars. Have a nice day and goodbye.